Chapter 2, which is chemistry and measurements. All good on volume, everything here? Yeah. So obviously in this chapter, we're going to get into things like taking proper measurements, which leads us really into a discussion about significant figures and how to calculate significant figures, think about significant figures and calculations. We will also talk in this chapter about conversions and doing conversion factors and a process which is known as dimensional analysis, which is a way in chemistry that they would like you to sort of work out problems where we see units and stuff like that. And towards the end of the chapter, we'll get into density and talk about density at the end of this chapter here. So let us get going. All right, so obviously units are extremely important. And whenever we take any type of measurement, it's always really important to not just have a number, but it should have some type of unit that's associated with it. You know, for example, if I just write 100, you know, what does that really mean, right? You know, the 100 is a number. It doesn't really give us the sort of reference for us to understand really what it means. If I have $100, that's very different than if I have like 100 pennies, right? Or if I have 100 apples, maybe somebody like apples, you know. So it's always important, especially in chemistry and especially in science, that we not only record when we take a measurement a number, but the unit is extremely important. And you should always have units associated with any type of measurement that you take. So you should always get into the habit in chemistry to include the units when you're taking measurements. Truthfully, for our purposes as well, when you're doing calculations and stuff like that, units are extremely important. They are very often left off by students as they're doing calculations. And, you know, they can really be helpful to help make sure that you actually do the correct calculation. So if you have the units there, you know what should be canceling, what's not canceling. You understand what units are left when you're done with the calculation. You just run through numbers. It's very common. People, for example, end up multiplying when they should be dividing when they should be multiplying, because they really don't know what they're trying to cancel out. So it's really important to always include units. When we think about units, there's actually kind of two types of units that we come across. One is sometimes referred to as the English set of units, and the other one is the metric system. For the most part, everybody in the world uses the metric system, except for us here in the US. We still use what is referred to as the English system. And you can imagine that that sort of creates a problem. As the world gets smaller, everybody sort of interacts with each other. Somebody is using metric system, somebody is using sort of the English system. There can be a lot of trouble that can occur in that situation. So believe it or not, like in 1960, they had a big conference on weights and measures. Sounds really exciting. And basically what they did is they came up with sort of a standardized system of units. And in chemistry, we oftentimes refer to this as the SI unit. The SI unit pretty much stands for the International System of Units, basically. And for the most part, it is based off of the metric system. And in chemistry, we oftentimes will see, and in your book, and even in your lab book as well, you oftentimes be asked for something like, what is the SI unit for mass? Or what is the SI unit for volume? And these are really sort of standardized units that, you know, at least in science, everybody can kind of use. Everybody's on the same page in terms of, you know, what these numbers really represent. So you'll see that a lot, SI units, really based off of that metric system. Now, that international system of units, you know, there are different units that we associate with different quantities. So not only including units in your calculations and your problems, which are really important to do so, it's also really important to make sure that you understand what those units mean, what that actual value means. For example, if we use a unit of L, which is liters, that unit tells us that we're dealing with some type of volume, which is different than if we see a unit of something like kilograms. That is a unit of mass. So as we go through these units in this chapter, and some of them will probably be, more recognizable maybe than some other units, sometimes people sort of forget the idea of understanding what does that unit really mean? What does it represent? And really in chemistry, like in a lot of life here, these are the major things that we look at. We have units that represent length, right, which is like distances. We have units that represent volumes. We definitely have units that represent mass. We definitely have units that represent temperature and time as well, are very common units. So it's really important. I can't tell you how many times over the years I've taught that, I have people come up and go, yeah, I had like 50 milliliters for my mass, and milliliters is not a mass. Or, I ask them like, what is the volume? And they go, it's like 32 grams. So you want to really make sure that you sort of understand, again, not only what the units are, but really what type of quantity they represent. So you know what you're talking about. Are you talking about a mass? You're talking about a volume, and so forth. So here are some of the common SI units for these different types of measurements that we make. The volume is a cubic meter. So in chemistry, we do see definitely liters a lot. We also see milliliters as a common unit. Cubic meters, truthfully, not so much, but we do see one that's a cubic centimeter, and that's what that represents. Now, how do we get a volume that's a cubic centimeter? It's actually taken from really 3 different length measurements. Centimeters are really length measurements. And if you have something like a cube, and you measure the length times the width times the height, and if you measure each of these in centimeters, each of the individual measurements there represent length. But when you multiply them all together, the centimeters times centimeters times centimeters, you end up with a cubic centimeter, which does represent a volume. So typically speaking, if you take any type of length measurement and you cube it, that will give you the volume of an object. Obviously, individually, each of those measurements in centimeters represents length that we see. By the way, we do definitely see cubic centimeters a lot in chemistry. Milliliters and liters are very common units of volume that we see. Also, by the way, a cubic centimeter is the same thing as a milliliter. It is a 1-to-1 conversion. So if you want to go from cubic centimeters into milliliters, it's basically the same number. You just change the units associated with it. And another one that we'll see probably down the road here, 1,000 milliliters is 1 liter. And those are very common sort of volume conversions that we do. Length, the meter is a very common one, and the SI unit is meter as well. We do see meters a lot. Centimeters and kilometers and millimeters are common sort of length measurements that we do come across. Mass is grams and kilograms, and that pretty much are 2 major units that we see for mass. When you go to a balance to weigh something, a balance is just a fancy word for a scale, right? So when you put something on it, we typically weigh it in grams. And a lot of times we will report certain masses in kilograms is a very common thing that occurs. Temperature, you're probably familiar with degrees Celsius, but pretty much 99.9% of the time, if you're doing some type of chemistry equation, some type of formula that needs temperature to be involved, it needs to actually be converted to a unit known as Kelvin, and that's what the capital K stands for. It's almost a safe bet, like a non-thinking thing, like I have a temperature, the first thing I should do is convert it to Kelvin, which obviously we'll talk about how to do that a little bit later on in this chapter, but that's almost a pretty no-brainer. Temperature typically does need to be converted to Kelvin. By the way, as we'll talk about when we get there, there is a difference. It is actually just Kelvin. We do not use the degree Kelvin, like we say degrees Celsius or degrees Fahrenheit. We just basically say Kelvin. So if we have something like 273 Kelvin, that's exactly how we'd write it. No little circle for degrees or anything like that. Time is seconds, which hopefully you're familiar with. I say that, by the way, there are some things you should be familiar with, right? Like time. That's right. So like there's how many seconds in a minute?
60.
And minutes in an hour?
60.
And hours in a day? It is 24, not 60, which is a very common mistake. A lot of people make, they go like 60 hours in a day. Sounds good. No, it really doesn't sound good. But you know, so keep those things in mind. So let's talk a little bit about volume. Again, a little bit more. Volume is really the space that's occupied by a substance. It is measured in units of meters cubed, but as I mentioned before, very common units that we do use a lot really are milliliters. Almost probably a majority of any type of glassware that you would take to take a measurement that is a volume is probably going to give it to you in milliliters. And so we very commonly will do that. And again, that's where, as I wrote on the other slide there, that 1,000 milliliters equals 1 liter is something that we definitely do use a lot. This is a graduated cylinder, by the way. That's a very good device to use to take measurements. By the way, whenever we take a volume measurement, and we'll get into sort of properly doing that in a bit here in this chapter, there typically is, and I'll exaggerate it here, a curvature of the liquid that you typically will see in a glass container. And the curvature of the liquid is really a result of the attraction between the liquid and like the glass container. So what happens is, in a lot of cases, there's a much stronger attraction between the liquid and the glass container than there is between the liquid and itself. And what that typically will do is cause the outside parts to kind of rise up the glass. And what that creates is what is known as a meniscus. And whenever you take a volume reading, you should always read it from the bottom of the meniscus. So you should always take that reading from the bottom of the meniscus. Now, sometimes it's a lot easier to see the curvature. Sometimes you can barely see the curvature that occurs, especially if you get into some type of glass where it has a really big opening, kind of really spreads out. It makes it really hard to see. But you should always try to practice when you do take a volume reading to try to find that meniscus. And it's always from the bottom of the meniscus. And the reason why we take it from the bottom of the meniscus is because these guys kind of climbed up the wall. It's only because of that attractive force. The actual volume is at the bottom there is really where it would be. If there was no attractive force, everybody would come back down. And that's really where the volume actually is in that particular container. Most of the time, probably 99.9% of the time, that is what a meniscus looks like, kind of a U. It can go the opposite way. A very common example of that is mercury actually goes the opposite way. And that's because mercury is much more attracted to itself than the glass container. So it comes in on itself. And we would always read here in terms of mercury, for example, actually from the top of the meniscus. So kind of, if you think wherever the kind of the U part is, you want to take from the bottom. Again, very rarely will you come across this, especially in real life, because they pretty much have taken mercury out of every chemistry lab I ever teach at because it's mercury. Nobody uses it anymore. When we started, I started teaching, we use it all the time, but they pretty much have taken it out. So probably 99.9% of the time, you're going to see that meniscus, you know, kind of doing that U shape. And you always want to make sure that you do read from the bottom of it. Again, here are some useful, what are referred to as equalities. Equalities are basically two things that are on different scales, but represent the same amount. So if you had 100 pennies and you have $1, represents the same amount of money. They're just on different scales. So again, as I mentioned before, this one definitely, this should be a quart. I'm not sure where the T went, but there should be a quart there. This one does actually pop up a number of cases sometimes, but you know, that liter to milliliter, definitely a conversion we use. I can't tell you how much time. Now, length, on the other hand, length is measured typically in meters. Very common units that we do use in chemistry is centimeters and millimeters. By the way, a ruler, right? Just remember how to read a ruler in most cases. Ruler typically on the top, those big marks are inches, yes? Yes. Been a while, but I think so. On the bottom, there's all those really small marks, right? And every so often there's like a big mark. And that's small marks. The big marks on the bottom, not counted correctly here, I was just doing some lines, are typically centimeters. The really small marks are millimeters. Yeah, there's 10 millimeters in a centimeter. And so the little, really small markings on the bottom of the ruler are millimeters. The bigger ones are centimeters. And obviously the inches are kind of on top, usually on a ruler, kind of spread out a little bit more. One conversion that we do see a lot is, for example, 1 inch is equal to 2.54 centimeters. So if you ever go to a ruler and find where the 1 inch is and just kind of draw a line straight down, that basically should be about 2.54 centimeters on the bottom part of the ruler. And that's a conversion we do see a lot, and that's one you probably should know. It's like everybody's favorite one to ask about length measurements is like, hey, 1 inch is how many centimeters? So 2.54 centimeters. Again, they both represent, in this case, the same amount of length. But again, they're just on different sort of scales. So let's talk just about some of these common conversions, as I just wrote on the other slide there, that 1 inch is 2.54 centimeters. This one definitely is used a lot as well. 1 meter is 100 centimeters. Not so much the inches and the yards and stuff like that, but again, you will definitely come across these. Again, some of these will be provided for you. I'm just sort of highlighting some of the ones that, you know, you do come across a lot, you know, as you take some measurements and for these different sort of quantities. Mass is the mass of an object is the measure of the quantity of matter that it contains. We do measure oftentimes mass on this guy here. This is one version of what's referred to as a balance. A balance is really, again, a fancy word for scale, is basically what it is. Some look like this, some have like a box of window over it where you kind of slide open the door and put some in there. These are what are referred to sometimes as being analytical balances. Analytical because they kind of give you a digital display there and a digital reading. Perhaps you're also familiar with, you know, if you ever gone to the doctor, right? They got kind of like the 3 beam type ones, right? They slide the weights around, or at the gym, right? In the locker room, they usually have those scales where you slide the weights around until the thing goes up and down until it sort of balances. Those are sometimes referred to as triple beam balances, and it sort of works the same way. Now, there is a difference between two words that are sometimes commonly used together, mass and weight. When we sort of measure the weight of an object, it does take into account the force of gravity. While when we take the mass, it's sort of independent of gravity. So if you weighed yourself here or if you weighed yourself on the moon, you would weigh different. But technically speaking, the mass in both locations would be the same because it's independent of sort of the force of gravity. So really important in science, and definitely important in chemistry, that when we do a process which is known as weighing, which sometimes confuses people, the process is known as weighing, but you really should refer to those type of measurements as masses. So we sort of take the idea that it's independent of gravity. So when we put something on a balance, you should refer to it as getting the mass of that object rather than the weight of the object. That's commonly what we do. As I mentioned before, probably most balances will give you the units there in grams, but kilograms is a very common unit that we do use in some calculations. There are, as we'll see probably on the next slide there, 1,000 grams is equal to 1 kilogram. So again, that is a mass conversion that we use a lot when we do it. By the way, just in general, I'm sure in lab you will be taught how to properly use a balance, but typically there's a button where we tear the balance. And when we tear the balance, it's like zeroing the balance. So you always want to start obviously with your balance 0. You ever use a balance where there's doors and windows, you should shut everything and 0 it. This, by the way, is what is referred to sometimes as a weigh boat. And it's pretty much what it sounds like. We use it to weigh out things like solids and stuff like that. So a lot of times what you'll do is you put your weigh boat on your balance, you then will 0 it, and then you can just put as much as you need and it'll tell you how much mass you are putting in there. You can also do sometimes, as you'll probably learn in lab as well, a process which is sometimes referred to as weighing by difference or mass by difference, where you weigh an empty container, take it off, fill it up, put it back on. You subtract the 2, which is just the mass of the container, and that tells you how much solid that you weighed out. So those are 2 very common ways that we sort of use a balance in real life. So I would say in terms of these conversions, obviously this one here and this one does pop up a lot, kind of going from English to metric there. 1 pound is 454 grams. That again is something that you'll probably use in a number of calculations along the way. You'll sometimes see 453.6, which is just the number I have in my head, but you know, it's the same thing. It's rounded a lot of times to 454. Now let's talk a little bit about temperature. There are really 3 different temperature scales that we do come across. Temperature measures how hot or cold an object is. It gives us also an idea of what is happening in terms of energy. Now, if something is absorbing energy, would we expect the temperature to go up or go down? We would actually expect the temperature to go up. So if something absorbs energy, everybody has a lot more energy, they're moving around, creates a lot more motion, and we see that reflected in the temperature as it starts to increase. Vice versa, if something sort of gives off energy, everybody kind of slows down, everybody's not moving as fast, and what we kind of see in the result of temperatures, the temperature will start to come down. There are really 3 types of temperature scales that we commonly come across, and that is degrees Celsius, degrees Fahrenheit, and as we talked about a second ago, our good friend Kelvin. Kelvin used to be called the absolute temperature scale. It was later named after a guy named Kelvin. That would be him. And again, out of these 3, this is definitely the one that we do use the most. Again, we do not use the degree symbol with Kelvin. We do with the others, but again, no degree symbol. The conversion between Celsius to Kelvin is one that we do a lot in chemistry, and I'm sure we'll see it here in a second. But if you want to calculate the temperature in Kelvin, you take the temperature in Celsius and you add 273 to it. The real number is 273.15. Most people don't keep the 0.15 because it gets rounded off most of the time. But if you want to keep it, you can. But the true value is actually 273.15 is the true conversion. But really, again, most people never use that 0.15. They just kind of use that 273. That also means, obviously, if we want Celsius from Kelvin, we do the opposite there. Temperature in Celsius would be the temperature in Kelvin minus 273. So the one here on top, definitely one that we use a lot in chemistry. Like I said before, pretty much every single formula that involves temperature, that temperature does need to be converted to Kelvin, which means you're probably adding 273 to the Celsius. I'll write it here, but I think it's probably on the next slide, but just in case. If we want the temperature in Fahrenheit, we take 1.8 times the temperature in Celsius plus a 32. So that is how we go from Celsius to Fahrenheit. And If we needed the temperature in Celsius, that would equal the temperature in Fahrenheit minus 32 divided by 1.8. Now, 1.8 is the same number that you get if you take 9/5. So maybe you learned the Maslow's conversions with like a fraction. It's basically the same number. If you need to go from, say, Celsius or Fahrenheit to Kelvin, you do need to go from Fahrenheit to Celsius, Celsius to Kelvin in that conversion sort of problem. I would say probably outside of chapter 2, you're never calculating Fahrenheit and Celsius in chapter 2 because it's about conversions, you will. But really the Kelvin to, or the Celsius to Kelvin is definitely the one that you should put into your head as to doing it. Again, you do need to know, you really need to know all three of these, this guy, and this guy, except that after chapter 2, you probably can forget about these guys for the most part. The top guy is really the one. Yeah, so for exams, you are responsible to know pretty much the formulas. There will be some conversions that will be given to you, something like, 454 grams as a pound, that type of stuff would be provided to you. Typically any type of constant value, for example, when we get into gases, like the gas constant would be provided for you. But for the most part, most of the formulas you do need to know for the exams and stuff. Again, when you look at the sort of review sheet, there are a couple of formulas that are given to you depending on the exam and stuff like that. So, some will be provided for you, but a vast majority you are responsible.
So, so those numbers, like the 273, like all those numbers, those are the formulas and will always be that. It will be like those numbers, right?
So if you're asking, are those the formulas for doing those conversions?
Like,
yes.
Not just for this example, but for what we gotta remember. Like it will always be those numbers. That's the formula.
Yeah. So these things I boxed are technically formulas that you need to know. And obviously they will change depending on what we're talking about. By the way, when we talk about sort of heat and energy, does energy move from hot to cold or cold to hot? Heat travels from hot to cold. So when we have heat, which again really, as it's moving around affects temperature, heat does travel from the hotter object to the colder object. The hotter object gets colder, the colder object gets hotter, and they might meet somewhere in between the temperatures, if they're sort of in an insulated container. Question on that.
Wait, can you repeat that again? Heat always travels.
Yeah, so heat always travels, that's right here. Heat goes from hot to cold. So it always travels from the hotter object to the colder object. By the way, while we're talking about heat and transfer of energy, when something gives off energy, our energy is released. That is what is sometimes referred to as an exothermic process. So when we say exothermic, it means that something has happened, that the reaction, for example, gives off heat and energy. You light a match, you can feel heat and energy coming off, right? That is an exothermic process, it's giving off heat and energy from the match to the surroundings, right? So the match is sort of like the system, everything else, the air is the surroundings, it's giving off all that heat and energy. When we have energy that's being absorbed, that is what is known as endothermic. So endothermic is a process where basically heat and energy is being absorbed. For example, if we take an ice cube out of the freezer and just put it on the table, that ice cube is going to accept all the heat and energy from the air outside, right? The surroundings. the ice cube itself will absorb all that energy. The result of that is that people start to melt, right? Because it absorbed all that energy, and that is a endothermic type of process. Questions on that? Now, time, as we talked about, again, seconds is a common unit of time, and for the most part, seconds is a lot of times the unit of time that we see a lot, but you are sometimes asked to calculate things in minutes and days, and as we just talked about earlier, hopefully you know those conversions and stuff like that. But if you think about, if you were doing an experiment, or most experiments that you perform, for the most part, we run these experiments not for a very long period of time, otherwise we'd be in the lab all day and days and stuff like that. So a lot of times when we do run experiments or do experiments, we oftentimes will measure time in the units of seconds because it's just very easy to sort of measure. So again, it's really important, as we talked about, to understand when we see units, what they really do represent. With that being said, take a minute here or so, and for each of these, identify the type of quantity we're talking about. Are we talking about a length, a mass, or a volume? So take. All right, so let's take a peek. So really, we want to look at, obviously, the unit here. So kilograms, as it kind of says right here, gives you the answer. Kilograms obviously is a unit of mass, so this would represent a mass. The person is 1.7 meters. Meters is a unit of length. So again, we're talking about a length here. And again, it may seem kind of silly, but I can't tell you, like I said earlier, how many times people really don't understand when they write a unit what it's representing. So it's really important to make sure you do. Grams is again a unit of mass, a very common unit of mass that we use. And lastly here, a bottle has 1.5 liters. Liters is a unit of volume. Any questions? All right. So, 3. So if we look at the, so the SI unit for volume, as we talked about, is the meters cubed. Again, remember that when we do cube that sort of length measurement, you can kind of think of it as like volume. Sometimes it's equal to the length cubed, sort of how we can kind of get to a volume. The SI unit for mass, again, is our kilograms. The SI unit for length is meters. And as we talked about, Kelvin is pretty much our go-to temperature unit. And again, like I said, as you go through this class or chemistry class, if you find yourself with a temperature value and you have not converted it to Kelvin, you probably missed something there in most cases. Very rarely, there's only one instance where I can think of a formula where the temperature remains in degrees Celsius. Everything else is pretty much going to be Kelvin. So something to keep in mind there. All right. We want to identify the measurement given by the SI unit. So take a second here. The SI, if you remember, basically, as I talked about, it is based off of the metric sort of system. So you want to really be looking here for the one that's more of a metric unit. Yard and feet are really English type of units. So our metric units should be the meters over here. Ounces, kilograms, and pounds, they are all, mass quantities, but pounds and ounces are really English type units. So here again, the kilogram is more of our SI unit. And again, all three of those obviously are temperature values there on the bottom. And as we talked about a number of times up to this point, our good SI unit there is our Kelvin. Again, you can see as written here, no degree like we see over here on the other two. Right? Any questions on? All right, so let's talk about measured numbers and significant figures. And one of the most important things that you need to know how to do in chemistry, life, is to properly take a measurement. Now, one thing that's really important to know is no matter what measurement you take, there's always some degree of uncertainty in a measurement. So whenever any type of measurement is made, there's some degree of uncertainty associated with it. The degree of uncertainty depends on the actual measuring device that you're using. So depending on the measuring device that you're using, you may have a really high degree of uncertainty, or you may have a very low degree of uncertainty. There's really two types of numbers that we'll talk about here in the next several slides. There are measured numbers, and there are exact numbers. So let's first talk about exact numbers as I see baseballs here. So, not that we're going to have a season the way it's going, but maybe we will. Let's see. Hopefully they'll get that all worked out. But if we had these two baseballs here, we would not do any type of experiment to figure out how many we had, right? We would simply just count them. So one way that we get an exact numbers are things that are counted. So clearly, if you had that, you're not going to figure out some weird scientific method to actually figure out how many are there. You're just going to simply count them. The other really more common way that we come across exact numbers in chemistry is through what are sometimes referred to as definitions, are really equalities. Like, for example, 1 inch is exactly 2.54 centimeters. So something like this. Any type of equality that we come across is considered an exact number. What that means is, as we will talk about a little bit later on in this chapter, might not make sense at this point, but you don't have to worry about significant figures when it comes to exact numbers. Exact numbers actually can have as many significant figures as you want, because they're sort of exact in counting and stuff like that. Now, measured numbers typically do come with some type of error, and measured numbers are made obviously when we make a measurement, and they have a specific number of what are referred to as significant figures based on the measurement. So let's just kind of look at a measurement, and we'll probably see a better slide in a second. Let's just see. Let's say this is a wonderfully drawn ruler. That is 1, that is 2. You'll quickly see why I failed art very quickly in this class, but I'll try my best here. So let's say these are centimeters here, and this is a ruler. And let's say we wanted to take a measurement, right? So we wanted to take a measurement, we'll call it like there-ish. So whenever you kind of look at something and you're using any type of piece of equipment, there's really two things that you want to look at when you're taking the measurement. You want to look at the actual scale that you see on it, and you want to figure out what does the big numbers represent. So clearly here, the big markings represent how much? 1 centimeter, right? This is 1 centimeter here, that's 2 centimeters. The big markings in this case represent 1 centimeter. If we count, and where we're going to start counting is actually not on the big mark. It's actually the one right next to it. So we're going to start counting right here. And if we count how many marks we have until we hit the next big mark, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between 1 and 2 centimeters. So there are 10 markings, which means each of the smaller numbers represent how much in this example. Each of the smaller numbers in this case represents not 1 centimeter, but 0.1 centimeter. That would make this guy right here 1.1, guy next to it 1.2, and so forth, all the way till you get to 2, right? Now, when somebody takes a measurement, there should be certain numbers that no matter who looks at it, everybody should agree. So when we look at this, that's 1.2, that's 1.3, 1.4, 1.5, and that's 1.6. So all right here, 1.6, no matter who looks at this, everybody should agree it is at least 1.5, right? No matter who takes a peek. And we would always want to record that 1.5. These are what are sometimes referred to as the certain numbers. Now we could clearly see, I say clearly in my bad drawing, but we could clearly see that it is not sitting like right on the 1.5. But even in my bad drawing there, you can also see that it is not exactly at the 1.6 mark, right? And that is where, in this particular case, the uncertainty in the measurement comes into play. Now, I may look at it and go, I think it's halfway there. I think it's like a 5, it would be halfway between the 2 points. Somebody else may look at it and go, I think it's kind of past the halfway point there. I think maybe it's like a 7. And maybe they would record 7. And clearly our units would go with it. And we would record 1.57. This 7 is what is sometimes referred to as the first uncertain number. So the 1.5 is what is referred to as the certain numbers. The 7 in my case is what is referred to as the uncertain number. And whenever you take a measurement, you should always record all the certain numbers plus the first uncertain number. And that is the proper way to take a measurement. When you do that, and you record all the certain numbers plus that first uncertain number, that is really what significant figures are. So in a measurement, when you do that, that tells you how many significant figures there are. That means in this particular case here, this would have how many significant figures? It would be 3 significant figures. I recorded all the certain numbers plus that first uncertain number. This guy here would have 3 significant figures. What does that mean? It means that there's uncertainty in this case to that second decimal point. It is assumed to be, in this case, plus or minus 0. In this case, 1. It means that, I'm not really sure where exactly that point is. I think it's 1.57, but it might be 1.58, might be like 1.56. It's somewhere in that area of uncertainty, but it definitely is in that area when we look on it on the scale there. Any questions on that? So as we'll see here as we go through this, it's super important to always look at the piece of equipment that you're using when you take a measurement. It does vary depending on the equipment. Even the same type of equipment will sometimes have a different scale. For example, very commonly, they buy the glassware on sale, right? So you can literally have 2 people that have like 10 milliliter graduated cylinders, same height, same size. One may go by 1 milliliter on the smallest markings, one may go by 2 milliliters on the smallest marking, even though they kind of look the same. So you should always look at your piece of equipment and try to figure out, what the big markings represent, what the smallest markings represent, and be able to take the reading to the proper digits. Any questions? Now, as we see here, we look at this, and in this particular case, our biggest numbers represent how many centimeters? Our big numbers here represent 1 centimeter, right? 1 to 2. Are there any other markings on this? There's not, which means our small numbers also represent 1 centimeter, right? They're actually the biggest and the smallest markings that you see on this particular case. That means we still follow the same thing here. When we look at this, again, no matter who takes a peek at it, it should at least be 4. So we would want to record 4. Now here's where we have to make an estimate. Again, it is not exactly at 4, not exactly at 5. In this case, it might actually look kind of halfway between the 2. And we would want to record 0.5 and a centimeter. And this would be our certain numbers This would be our first uncertain number. By the way, sometimes people refer to the first uncertain number as the estimated digit. So sometimes they refer to it as the estimated digit. By the way, that would mean in this particular case, how many significant figures would this have? Would have 2 significant figures in this particular case. Again, the uncertainty here lies in the 0.5 or the first decimal place. Basically, what we're saying is, hey, it might be like 4.6, might be like 4.4, which if you look at where it's sitting is approximately in that area where it would be. Good questions on that. Yeah.
Could you, how do you get the
Two significant
Uh-huh.
figures. So whenever you take a proper measurement, that's the key to that, by the way, you got to take a proper measurement to the proper number of digits. You should be recording all the certain numbers plus the first uncertain number. And when you do that and you take a measurement like that, which is how you should do it, all those numbers are what are referred to as being significant. And that's how we get it. So that's what we did here, which means both of these numbers here are considered significant and they are what are referred to as significant figures. So whenever you take a measurement and you do that, all the certain numbers plus the first uncertain number, that is basically your definition of what significant figures are in a measurement. Other questions? Yeah.
Will you ever ask us to point out like the first uncertain?
Yeah, you're gonna have to do that. I know for sure in lab, there's a question that asks you to do that. And yeah.
And when you do that, would you just put for this case to be 0.5?
Yeah, so I'll give you the answer like this. If you wrote 0.5, I would understand that you know it's this digit. Yeah.
Okay.
You probably want to do it however sort of displays it to the right digit. Sometimes people will want you to write like, 0.1 units of that or something like that. But yeah, so you would want to identify. By the way, as we'll talk about a couple of times probably as well, the estimated digit, if you will, or that first uncertain digit is not always the last number in a number or a value, but it is always the last significant figure. So there is a difference in what I just said. It may not make sense now. We'll see an example, I think, as we go through it. But when you're asked to figure out the estimated digit or that first uncertain digit, what you want to figure out is how many significant figures there are in that number, and it should be the last significant figure. 9 times out of 10, it is the last number written, but it is not always the last number written. So it is really the last significant figure versus just the last number that you actually see written. Now, if we take a reading, for example, right out of the screen. Hopefully not. All right, we'll pretend it's way up there. All right, these are milliliters. I did. Okay, I kept on the screen. All right, it's on my screen. I want to make sure. All right. So this is 10 milliliters. We're gonna you want to count actually starting with the next smallest little dash past the big dash. So we would start counting the smaller dashes here. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 dashes. Obviously, in this particular case, and by the way, we'll make this milliliter, so I'm going to do a meniscus kind of move-ish. So big numbers here on this, if this was a graduated cylinder, is 10 milliliters. Right? There are 10 dashes between 10 and 20. That means each small dash is how much? 1 milliliter, right? This would be 11. Right? This would be 12 in this case, this would be 13, and so forth. Now, when we take a reading here, again, not the greatest drawing, but I'm going to go for the bottom of my meniscus. We should see again, it is at least 13, right? Again, not exactly to the 14, which is hidden up here. So we do need to take an estimated digit. And in this case, again, maybe you want to go with 7 milliliters. The 1 and the 3 are the certain digits. The 7 here is our estimated or uncertain digit. This guy would have how many significant figures? would have 3 significant figures.
Where you get that 3? Is it because there's the 3 right there?
No, it's because if we count all these numbers, that's 1 number, 2 numbers, and 3.
Oh, okay.
So when you take a proper measurement, you should have recorded all those certain numbers and that uncertain number, taking all those numbers that you recorded in a measurement. Because you took that measurement, they're all important if you want to think about it that way. They're all what are considered significant.
Okay, so when you say what are the, if there's 4 numbers and you say what are the significant figures, it would be 4.
It should be all of them. If this is a measurement, so like this.
I mean,
measurement-
yeah, like if it was a measurement.
Yeah, like this measurement on the bottom here, there's 1 number and 2 numbers. They're all significant. And that has 2 significant figures.
Oh, okay. So if it had just 4 for
If
example,
you
it was-
record, if you technically took the measurement correctly, you
Yeah.
recorded 4 digits, they all should be significant.
Okay.
I have a question.
Yeah.
What if it's, for example, 13.7, what if it's 03.7? Would that only be 2 significant figures?
3.7.
Yeah. for
Yeah,
example.
you probably want to put the 0 before the 3. There are numbers where you have a 0 before a decimal point. And we're going to talk about how the rules for looking at numbers and figuring out how many significant figures in just a second. Just want to talk about taking the measurements right now, but we'll get to that question in just a few slides, I think, down the road here. But there are certain rules that when you look at a number, there are certain rules to help you decide how many significant figures that number is. I think is your question. And we'll talk about that. And the zeros is really the thing that sometimes gives people a problem. But first, I want to focus in on taking proper measurements here. Any questions on that? By the way, is it important to take a proper measurement? Does it mean anything if you don't? Well, let's just say, for example, we went back to like this example here, where this is 1. So this is kind of like the ruler we had 4, right? And let's just say we were measuring something and it was like dead on that number right there, that tick mark right there. We would want to do the same thing. So this is the same ruler we started with, right? We got 1 centimeter difference on the big numbers. There's 10 dashes between, which means each one is 0.1. That means right here is 1.1, 1.2, 1.3, and 1.4 right there. So would we want to record 1.4 centimeters? Would we want to record 1.40 centimeters? Would we want to record 1.400000 centimeters? I'm going to say no, that feels like a lot of zeros. Right? So is there really a difference in how we report the number when we look at these 2 numbers? So let's see if there really is. Let's first start with, if we took each of these measurements and going under the assumption that we took the measurement correctly, how many significant figures would that number have? It would have 2 significant figures, right? The uncertain number or the estimated number would be which number? There is no 0 in the one above. There is a 4, right? It would be the 4, right? So what this measurement tells us is, I think it's 1.4. This is where my error is, but it could be maybe like 1.5 or as low as like 1.3, right? That's where the errors are lies. If we look at our chart, we can see that that line is nowhere near 1.3, right? And nowhere near 1.5. So by lopping off this measurement here, this 0, we just made that measurement pretty crappy. Yeah, it's a very bad measurement. You just increased your error by a lot. What we should record is actually what's on the bottom here, this one. Because what this tells us is how many significant figures would this number have? It would have 3 significant figures in this case. The 1 and the 4 would be our certain number. The uncertain or estimated number would be the 0 here. What this tells us when we record 1.40 is maybe it's 1.40, but hey, maybe it's like 1.41 where that arrow is, or maybe it's like 1.39. And now looking at our actual measurement, that's more realistic what we are seeing there. based on the scale. So sometimes people think, well, it's not that big of a deal. I just lop off the 0 and it looks like it's right on there. But you have a tremendous more error here because you lopped off a significant figure because it's kind of important. And you made your measurement 100% worse than it should be. So you never want to sort of lop off the 0, even if you feel like it hit dead on a line. And if you have the ability on that piece of equipment to take the reading to 1 decimal place, 2 decimal places, however many decimal places, you should put the 0 in there to maintain basically the error. And if you take out the 0, for example, like we did here on the left, you really just made it a tremendously worse measurement. You created more error that you shouldn't have, and it makes it a crappy measurement. So there really is a big difference. Again, we shouldn't record it like this. We should record it as 1.40, even if it's dead on the number. That maintains the proper number of significant figures. It also tells us really where the error is, which is in that second decimal place. Question on that. Now, yeah.
Okay, so when you are absolutely sure that that's that number, you should add that 0.
You absolutely should in a case like this, because if you don't, what you're saying is the error is not really in the second decimal place. It's actually in the first decimal place, which then is actually incorrect based on the equipment. And you just said, really, my measurement is pretty crappy. I have a lot of error, right? There's a really big span between 1.4, 1.5, and 1.3, as opposed to it's somewhere in like 1.40, 1.41, 1.39. It's a much better measurement, that second one, and it's the correct measurement based on the piece of equipment. Now, you could not do that measurement, for example, in the previous one, because we did not have the ability to do that. So the best that we could do on the one here on the bottom is take it to the first decimal place. Same thing here, if you hit right on the 4, and you just recorded 4, for example, we just said, I'm just going to record 4 centimeters. The certain digit here is
4.
the uncertain digit is also 4. Yeah. And so what you're saying here, if you just recorded 4, you're saying, well, I think it's 4, but maybe it's 5, which it really isn't, right? Or maybe it's 3, which it clearly is nowhere near 3, right? And you just created a lot more error. You created a worse measurement and a wrong measurement. And that's why here, this guy would actually only have 1 significant figure, but you have the ability in this case here to take it to that second significant figure, and that's why you should record it. So it's really important when you take measurements, and it happens a lot, people just like lop off numbers and go, yeah, it's not that important, but it really is important. And every number that you lop off and you would technically should record, you're basically making your measurement worse and worse when you do that. Now, if you ever take a measurement that is something that is digital, like the balance we saw earlier on in that picture, you should always record all the numbers. That's also a very common mistake that people make when they're in the lab. They go weigh something on the balance and go, yes, it says 52.566 grams. Yeah, 52 seems good, right? And you're also, again, making that measurement worse. So anything that is digital, all the numbers that it shows you are important, and you should always record all the numbers on any type of digital display. Questions on that? So what have we learned in terms of measurements? There is a general rule that you could follow. Typically speaking, if you look at what we did, the smallest marking here was 1 centimeter. We were able to go 1 more place to the right of the smallest marking to take our measurement. We were able to go 1 more place to the right. Smallest marking up here was 1 milliliter. We were able to go 1 more place to the right to take the measurement. Typically speaking, you could go 1 more place to the right of your smallest marking. So for example, here, same idea, smallest marking was 0.1. We were able to take the reading to 1 more place to the right. So a good thing to keep in mind is when you figure out what the slowest marking represents on your piece of equipment, you could usually go 1 more place to the right of it, and that's what you should record. Again, if you hit right on the number, you should record that last place as a 0, or that is really where your estimated digit is. Any question? Now I say most of the time, and that is the case, nothing's 100% here. For example, if we had something like this. All right, so let's say we had a graduated cylinder like this. Big marking is 10 and 20. So big marking in this case is how many milliliters? 10 milliliters. There is in this case one small marking, 2, 3, 4, and 5. There are 5 markings between 10 and 20. What does each little mark represent? Yeah, the smallest markings in this case represents 2 milliliters, right? That is 12, 14, 16, and 18. Now, when I take a reading here from my bottom of my badly drawn meniscus, somewhere in this region, I am between 14 and 16. In this case, what is between 14 and 16? It's 15, right? You can only actually go in this case to the whole number, which means that this would have how many significant figures?
2.
Yeah. The uncertain or estimated digit would be the 5, which means it could be 16, could be sort of in that 14, and that's where the range of error is. In this case, you don't have the ability to go one more place to the right. The reason for that is if we blew it up, that is 12, that is 14. There's not enough room on the scale to figure out where 12 ends, 13 begins, you know, and so forth. There's not enough room, I'm sorry, this or between the little those two. There's not enough room in that particular case to figure out where sort of 12 ends, 13 begins. There's not enough space to visually do that. So this is a rare exception. I would say 99% of the time, you can take the reading one more place to the right of the smallest digit when you do that. Any questions on a properly take a measure? Here, again, if we look at this, we have biggest units here are 1 centimeter. There are 10 markings, so our smaller guys are 0.1 centimeters. Again, here, everybody should agree it's at least 4. That is 1, 2, 3, 4, 5. So that is our certain numbers there that they recorded. Again, here they feel it's maybe not exactly on the 5, maybe it's a little bit over. That would be our first uncertain number. In this case, as we see again, we could go one more place to the right of the smallest digit. And they recorded 4.55, and that would have how many significant figures? 3. It would have 3 significant figures. Here again, no marking, so biggest marking, smallest markings, 1 milliliter. Here we are dead on that. So as we talked about the very first one, we don't want to just record 3 because that implies that the error is sitting there. We want to maintain that digit. And again, this now will have 2 significant figures with the estimated or uncertain digit being there. Again, basically telling us maybe it's 3.1, maybe it's 2.99. And again, if you visually look at it, that is pretty realistic from what we're seeing here. Again, if you just recorded 3 milliliters, that would be 1 significant figure. And I would say it could be 2, it could be 4. And again, you could clearly see it is nowhere near that in terms of the error. So really, really important to maintain the proper number of significant figures when you take that measurement. All right, so let's take a look at this one. I'm not sure if anything shifted. All right, so take a second and record the red line. All right, so let's take a look. So we want to kind of look at the big scale again. The ruler kind of moved a little bit, but I believe that's a 9 there, and next biggest marking is 10. So the big marking there is our 1 centimeter. If we count the dots between the 9 and the 10, there should be 10 dots. And that means, again, the smallest markings here are 0.1 centimeters. Looking at my red line, I'm going to go with this is 9.1. That's 9.2. Almost looks pretty much right on that. That is 9.2. Should I record anything else in this case?
With the zero.
I should record a 0. Again, I have the ability to do so because of the markings. I'm able to go one more place. Here I do feel it looks like it's right on that line. We do want to record that 0 and the unit. This would have how many significant figures? Right. The uncertain digit would be,
Zero.
it would be the 0, right? That's the main digit here. Any question?
Is there a time when you shouldn't add the zero? Like in this case, or like, it was like a point something, is there a time when we shouldn't?
So we only want to add the 0 if you feel, for example, two things. So you want to add the 0 if you feel it's like right on the line, okay, or right on a mark, whatever marking may be. And you have the ability on that piece of equipment to go one more place to the right. So there's just two things sort of involved in that, you know. In most cases, you can go one more place to the right, and if it does hit a marking right on the nose, you should have the 0. Because really what the 0 here is doing is maintaining really the kind of error of the equipment, right? The how good or bad of a measurement it is. Again, if we just did the 9.2, it would have how many significant figures?
2.
Yeah, it would have 9.2 would have only 2 significant figures, which means the uncertain number would be the 2. Which what we're saying here is this could be like 9.3, or it could be like 9.1, which clearly it's nowhere near there, right? And by leaving that 0 off, we made the measurement wrong to begin with, but really worse measurement it should be. So if you have the ability to go one more place to the right, you feel it's like dead on a number, you do need to maintain the 0 there to keep the measurement correct in terms of how far you should take it. Other question?
So when you say like if you could go more to the right, you mean because there's all those other
Yeah, so
lines, right? So
typically speaking, looking at the smaller markings, you typically could take the reading to one more place to the right of the smallest marking. And again, I would say probably 9 times out of 10, you'll be safe to do that. You know, there's a very few rare occasions like what I just drew a second ago that you can't really do that. But pretty much it's almost a no-brainer. You could go one more place to the right. And again, I won't say 100% of the time, but probably 99% of the time you'll be in good shape. Other questions? So let's talk about significant figures in a measured number, as I talked about. The significant figures are what happens when we record pretty much all the certain numbers plus the first uncertain number, like we've been doing. So earlier there's sort of a question about, you know, would a 0 be significant or not? So let's talk a little bit about the rules for counting significant figures. First off, first rule for counting significant figures, any non-zero number is always going to be significant. So if I have a number like 1, 2, 4, 5, this would have how many significant figures?
4.
Would have 4 significant figures. By the way, that is also where you start counting. So when you look at a number or measurement, you start on the left and you start counting significant figures as soon as you hit the very first non-zero. So in this case, this would be the very first non-zero. At that point, we would start counting 1, 2, 3, 4. Zeros is what gives people sometimes a very difficult time. So let's talk about the 3 different types of zeros. There is what is sometimes referred to as a leading 0. Those are not significant. Those are all the zeros that come before you hit the very first non-zero number. So for example, 0.0000111. This would have how many significant figures if this is a measurement?
3.
It would. All these zeros are not significant. I would not start counting until I hit the very first non-zero number. And then obviously the rest of them are non-zero as well. So this would have 3 significant figures. Questions on that?
The leading 0, right?
Yeah, that's a leading 0. By the way, the uncertain number here would be the very last one. Yeah, that would be our last significant figure. There are what are sometimes called trap zeros, or captain zeros, those are significant. Which means if I had 4004, how many significant figures would it have? It would have 4. We would start counting here. That's our first non-zero. These zeros are trapped, so they are significant. And obviously that's a non-zero at the end, so that would have 4 significant figures. Questions on that there? The last zero is really the one that gives everybody the hardest time. They are what are referred to as trailing zeros. They are the zeros that come at the end of a number. They could be significant or they may not be significant. What makes trailing zero significant is, I'm just going to use this to write on, trailing zeros are significant if there is this stuff there, a decimal point in the number. So zeros at the end will be significant if there's a decimal point in the number. By the way, the decimal point does not need to be near the zero, just needs to be in the number somewhere. So for example, if I had 0.00100, how many significant figures would this have? You would have 3. None of these zeros are significant. They're all leading zeros. That is because it is not until we hit here. That first one is my first non-zero. That's why I technically should be counting. That is significant. These are now zeros that come at the end. They are significant because way down over here, there is a decimal point there, and this would have 3 significant figures. What happens if I had 600? How many significant figures would it have? It would have 1 significant figure. That is a non-zero. These are zeros that come at the end. Do I see a decimal point?
No.
I don't. It would have 1 significant figure. If I wrote 600 like this, how many significant figures would it have? It would now have 3. This is significant. These are at the end, which are now significant because the decimal is actually written there. This would be 3 significant figures. Now, where is the estimated digit or uncertain digit in this number?
The last zero.
6.
I hear 6 and 0. That's all the numbers that are up there. There are no more. So let's see. Nobody said 5, so that's good, right? All right. This would have how many significant figures?
1.
1, which means the estimated digit is
6.
actually the 6. That means, as we talked about this measurement, if this was a measurement, you're saying, well, I think it's 600, could be 7, could be 500, right? Pretty crappy error there, right? Pretty big error. And the estimated digit is actually the 6 here, which, as I was saying earlier, is not the last digit written, right? But it is the last significant figure written, right? The estimated digit on the guy on the bottom would be 0. It would be the last 0, right? And this measurement is saying, I think it's 600, but maybe it's 601, maybe it's 599. That estimated digit there is that last 0. And again, the better measurement would be the one on the bottom, right? A lot less error involved in that measurement. So this is an example, as I was talking about earlier, that, you know, it's not always the very last digit that's written is the estimated digit, but it is always the very last significant figure that's written is the correct number of significant figure. Any questions on that? Yeah.
For the trap zero, would it matter if there was a decimal in it? So like if it was 4.004?
Say it one more time. 4
For
point.
the trap zero, where you gave the
Yeah. Give me your number. 4 point.
4.004
How many significant figures would that?
out of the 4.
It would still be 4. It doesn't matter. This decimal would only matter if there was a 0 after that last 4. So if I laid up a couple more zeros, it then would have. You would have 1 significant figure, 2, 3, 4, and now 5 and 6. These would be significant because of the decimal point that's in the number. Again, the decimal point does not have to be near those zeros, but in terms of the trap zeros, it really doesn't matter. As long as they're trapped between 2 non-zero numbers, they're going to be significant. Other questions? All right, hey, that was fun. Way up there. All right.